So in the last video, we looked at addition of complex numbers and multiplication of complex numbers and subtraction of complex numbers, but we didn't look at division of complex numbers. And that's because first, before we do that, we want to look at this idea of the conjugate. So just like the conjugate of sums of surds, so root 3 plus 1, the conjugate would be root 3 minus 1, we have conjugates of complex numbers. So it's denoted as z with a line above it, and it's just a minus bi. And you can see if we have a plus bi and a minus bi, that's a sum of perfect squares, like we explored in the previous video. So a plus bi, a minus bi is going to be a squared minus abi plus abi minus bi squared, which is just a squared plus b squared. Note that when a complex number and its conjugate are added together, a real number is the result, because we're going to get a plus bi plus a minus bi. We'll get 2a plus 0i, which is just 2a. So graphing complex conjugates, they're a reflection of z in the real axis. If you take the imaginary component and you make it negative, if you're in the top half of the Argand plane, you'll end up in the bottom, and vice versa. So, properties of conjugates. If you take the conjugate of the conjugate, you get the original function. If you add two numbers or subtract two numbers and then take the conjugate, that is the same as taking the conjugate of the sum or difference. The sum or difference of the conjugates. The conjugate of the product is the product of the conjugates, and the quotient, the conjugate of the quotient is the quotient of the conjugates. So z1 times, conjugate of z1 times conjugate of z2, and then also conjugate of z1 divided by conjugate of z2. So write the conjugate of each of the following complex numbers. So for part A, we're going to get 8 minus 5i. For part B, we're going to get negative 2 plus 3i, that's a weird 3, plus 3i, and then we're going to get 4 minus I root 5. Example 12, if z equals 5 minus 2i and w equals 7 minus I, show that z plus w conjugate is z conjugate plus w conjugate. So show that the conjugate of the sum is the same as the sum of the conjugates. So z conjugate is equal to 5 plus 2i, w conjugate is equal to 7 plus I, so z conjugate plus w conjugate is equal to 12 plus 3i. Z plus w is equal to 5 plus 7 plus negative 1 minus 2i. That's going to give us 12 minus 3i as we expected. Therefore, the conjugate of the sum is equal to 12 plus 3i, and therefore the conjugate of the sum is equal to the sum of the conjugates. But we can only say that for what we proved, when z equals that and w equals that. Even though that we know it works for everything, just in terms of clarity of the question, we should restate the initial conditions. Alright, so this leads us to the division of complex numbers. So if z and w are complex numbers in the form a plus bi, then z over w can be expressed in the form a plus bi by simplifying z over w times the conjugate of the conjugate. So this is kind of like rationalizing the denominator, but instead of rationalizing it, we're making it real. So realizing the denominator. So express 2 plus I over 2 minus I in the form a plus bi. So 2 plus I over 2 minus I, we want to multiply by 2 plus I on itself. So this gives us, in the numerator, 4 plus 4i minus 1. And in our denominator, we're going to get 4 plus 1. So this is going to give us 3 fifths, because we got that minus 1. 3 fifths plus 4 fifths I. Notice that I still represent it in a plus bi form. I don't put the 1 over 5 out the front. I don't put it as 3 plus 4i over 5. Because it's a real number, I can now represent it as two fractions. So let's just put in our equal signs and leave it at that. Example 14. If z equals 3 plus I and w equals 2 over 4 minus I, determine imaginary of the difference of 4z and w. So 4z we first need to find, which is just going to be 12 plus 4i. We then need to find what w is in the form a plus bi. So we take 2 over 4 minus I, we multiply it by the conjugate of the denominator, 4 plus I over 4 plus I. So in our numerator, we're going to get 8 plus 2I. Our denominator is going to be 16 plus 1, because it's the addition of two squares. So that is going to give us 8 17ths plus 2 17ths I. So 4z minus w is going to be 12 minus 8 17ths plus 4 minus 2 17ths I. Therefore, the imaginary component is equal to 4 minus 2 17ths, which if we were to write it as a fraction, 4 times 17 is 34 times 2 is 68. So 68 take 2 is 66 on 17. Or 3 and 15 17ths is the other way to look at it. All right, example 15. Prove that the conjugate of the product is equal to the product of the conjugates. So what we're going to do is let z1 equal a plus bi, let z2 equal c plus di, and then we're going to treat it as a left-hand side, right-hand side proof. So the left-hand side, we want to take our product, a plus bi times c plus di, and then take the conjugate of the whole thing. So that is going to give us ac. It's going to give us plus adi plus bci minus bd. We want to take the conjugate of that, but to do that we need to know what's the real and what's the imaginary. So our real component is AC minus BD. Our imaginary component is AD plus BC. And so if we take the conjugate of that, we're going to get AC minus BD minus IAD plus BC. So let's see what the right-hand side looks like. So right-hand side is going to be A minus BI times C plus DI. Sorry, C minus DI. That's going to get us AC. It's going to get us minus ADI. It's going to get us minus BCI. It's going to get us minus BD, because our two negatives cancel out, and then we get I squared, so that's still negative, which can be represented as AC minus BD minus, let's put our I in there, minus I AD plus BC. And hey, look at that, left-hand side is equal to right-hand side. Therefore, the conjugate of the product is equal to the product of the conjugates. All right, next idea that we're looking at, and this will end the video for today. Given a non-zero complex number z, there exists a complex number w such that z times w is equal to 1, with w being the multiplicative inverse of z, denoted by w is equal to z to the negative 1, which is equal to 1 over z. So hence z times its inverse is equal to 1. So z inverse is equal to 1. Therefore, we're going to get 3 plus 4i times 1 over 3 plus 4i is equal to 1. So therefore, z inverse is 1 over 3 plus 4i. However, this is not in the form a plus bi, so we have to convert it. So z inverse is equal to 1 over 3 plus 4i times 1 in the form of its conjugate over itself, So I say 1 in the form of because I want to recognize that we're not changing the value of this fraction. We're not multiplying it by a scalar, we're multiplying it by 1. We're just changing what it looks like. So our numerator becomes 3 minus 4i. Our denominator becomes 9 plus 16. So this becomes 3 on 25 minus 4 on 25i. And we can see there, in general, if z equals a plus bi, then the multiplicative inverse is a minus bi, so 3 minus 4i that we saw there, over a squared plus b squared, because that's the sum of perfect squares that we've been looking at. And so in our case, that's going to be 3 on 25 minus 4 on 25. Thank you very much for watching.